So now generally composite materials are classified into number one, polymer matrix composites. Number two, metal matrix composites. Number three, ceramic matrix composites. Number four, carbon-carbon composites. These are the four major broad categories of composites, right? Mm, and in this Gus lecture, I will be dealing with two types basically. Number one, I will deal about the fundamentals of metal matrix composites. Number two, I will deal with unidirectional fiber reinforced composites, polymer matrix or anything like that, right? Where it is fiber reinforced. In the case of metal matrix composites, I will deal with particulate metal matrix composites, where the reinforcements are particulates. In the case of, I think all of you are able to hear me well. Huh? Huh? My voice is audible for everybody. Very good, very good. So I will deal two cases where one is metal matrix composites, where the reinforcements are particulates, and the other case, sorry, and in the other case, I'll deal with fiber reinforced composite. So two cases I will deal, right? So in the case of metal matrix composites, again, there are two classifications. Number one, in situ composite. Number two, ex situ composite. What is the difference between ex situ composite and what is the difference between in situ composite? What is the difference between ex situ composite and in situ composite, right? In the case of ex situ composite, the reinforcements which are already available are mixed inside the molten metal, poured into the molten metal, thoroughly mixed, and then it is cast into molds, right? So that is ex situ composite. That is externally formed reinforcement is mixed into the molten metal and thoroughly mixed, and it is poured into mold, and it is called ex situ composite, right? In the case of in situ composite, the two halide salts will be there. For example, titanium and boron salts may be there. One titanium bearing salt will be there, and one boron bearing salt will be there. These two will be in powder form. They will be mixed already. They will mix first, and then the mixture of powder is poured into, slowly dropped into the molten metal, right? But this powder is not reinforcement, right? These are chemicals only, right? These two powders in the presence of molten metal, they will react together, and the reinforcement will form inside the melt, right? So this is called as in situ composite. If the reinforcement is already formed externally and mixed into the melt, it is called ex situ composite. And if the reinforcement is formed inside the melt by reaction, it is called in situ composite, right? For ex situ composite, the example is aluminum silicon carbide metal matrix composite, or alumina Al2O3 composite, or aluminum zirconia composite. All these are examples for ex situ composites. Whereas for in situ composite, the example is AlTiB2, aluminum titanium diboride. Aluminum titanium diboride composite is the example for in situ composite. Generally, in the case of in situ composites, when the halide salts react with one another, it will be exothermic. Heat will be generated, right? So when if the salts are poured mixed at a rapid rate, then the temperature will shoot up enormously, right? And the temperature will become uncontrollable, right? So we should drop it slowly in such a way that the melt temperature is almost maintained. It is not because the heat transfer through the crucible should be equal to the rate at which the salads also dropped, right? Only then the temperature can be maintained, right? Otherwise, temperature will drastically shoot up, and crucible and all will be at risk, because crucible itself may melt or it may break or something like that may happen, right? Because generally in aluminum TA-bit composite, the melt should be maintained somewhere around 800 to 825 degrees centigrade, right? So if you go beyond 825 degrees centigrade, then there is a chance for crucible itself to break, because the crucible will become red hot, and there is a possibility that the crucible is breaking, right? Whereas in the case of Exito composite, the temperature will not go shoot up like that, because nothing exothermic is there, right? When the SiC, generally, if AL-SiC composite is taken, the temperature, belt temperature will be somewhere around 700 degrees centigrade only, right? In the case of cast metal like A356, the melt temperature will be somewhere around 700, somewhere around 700 degrees centigrade only, right? Whereas if you take ductile metal or what to say, uh, wrought metal, ductile or wrought metal, like for example AL6061, the belt temperature will be somewhere around 800 degrees centigrade, right? 780, 800 degrees centigrade, 780 or around that, right? Because at around it will be 780 to 80, 800 degrees centigrade, because rod metal, the melting temperature is more, right? Whereas for cast metal, the melting temperature is less. For A356, the melting temperature is around 670 or 680 degrees centigrade only. Whereas for AL6061, the melting temperature is more than 750 or around 770 degrees centigrade. And so we have to maintain it at a temperature more than this. So around 780, 790, like that we will maintain, right? These are the differences between various types of when we process different kinds of metal matrix composites. In the case of, even in the case of matrix being aluminum itself, right? For ALS, for A356 SiC composite, the melt temperature will be somewhere around 700 degrees centigrade. For AL6061 SiC composite, the melt temperature will be around 780 or around that. Whereas for ALTAB2 composites, the temperature will be around 800, 825, between 800 to 820 degree, around like that, 825 like that. If you go beyond 825, there is every chance that the graphite crucible is breaking, right? Because it will become red dot, and it will become unstable at that particular temperature, and the crucible will lose its strength, right? So if the crucible breaks, there will be some accident, and so it should be avoided, right? These are the fundamental things which I wanted to say, right? Now, with in now we'll see two cases, right? In the case of metal matrix composites, where the reinforcement is particulate, right? We will see what is the strengthening mechanism, right? And in the other case, in case two, we'll take a unidirectional fiber reinforced composite, and we'll see, if you know the elastic modulus of fiber and elastic modulus of metal, then how we can calculate by rule of mixtures. We'll derive the rule of mixtures also, right? And see how we can estimate or calculate the elastic modulus of the composite even before it is cast, theoretically, right? We can estimate it, how much it may be like that, right? We'll see both the cases, and even before going into, we'll first take case one, right, where we'll take a particulate metal matrix composite, right, and see how the strengthening mechanism is. I will discuss on that, right. Even before that, what I want to say is, there are some fundamentals which have to be dealt, that how strengthening or plastic deformation is taking place. In the case of metals, I will just touch up on it for 1 hour, for a few minutes, and then I will go into the strengthening mechanism, right? So now I will go into the PPT, and 1 minute. இப்போ ரெக்கார்ட் பண்ணீங்களா? அப்பயே ரெக்கார்ட் பண்ண ஆரம்பிச்சு. So the PPT, the title of our presentation is Fundamentals of Composites, right? So now I'll go to slide 1. So we'll see what are dislocations first and the importance of dislocations, right? So here in the figure 1, in the left side extreme figure, right? There are so many atoms, right? A line of atoms are there, right? Like this, so many lines of atoms are there, right? So here, let us assume, see, we will take this particular line of atoms, right? And then here in the dark, the atom, three atoms are shown darkened, right? So, are in black color, right? So these three atoms, there are line of atoms like this, right? Lines of atoms like this. Out of this, let us assume this in this particular column of atom, only three atoms are there, and the remaining atoms are missing, right? So a line of atom itself is missing, right? So because of this, see the previous row, it will it will that will also not be in the straight line. That will come slightly inside, right? And it will occupy a position like this. If you see, there is a tilt here, right? And there is a deviation here, and it comes closer to the mid row, right? So, so this particular see this in this, see in this I am showing with the cursor, right? So the dark line of atoms before that, the previous one or the first one, this row of atoms, it is coming straight up to this point. Then the remaining part of it, right? Because there is more gap here, right? They get dislocated, right? And it occupies some other line, right? And these two are not in the same vertical line. The top three atoms and bottom three atoms are not in the same vertical line, right? And the bottom three atoms are dislocated, and they occupy some different position, right? So like this, the dislocated atoms, the line of dislocated atoms is called a dislocation, right? And now we'll see how in the case of ductile metals, deformation is taking place, right? Here we'll see there are three lines of atoms here, right? Three columns of atoms. In the second, the figure 2, right? The sketch 2, in the left side, there are three rows of atoms, long row of atoms, right? And then there is the three atoms are shown in the mid plane, right? And after that, some three atoms are missing in that particular column, right? So here, see, let us assume from left, see in the top half of the whole crystallographic arrangement is pushed from left side to right side, right? And on the opposite side, on the bottom side, it is pushed from right side to left side. It is pushed from opposite directions, but staggered, right? Here what happens is, when it is pushed like that, right, the top atoms will be pushed from left to right, and from the bottom atoms are pushed from right to left. Because of this, what happens, see, as it is pushed here like this, see here in the second figure, see there the see the bottom ones, right? See here, the bottom, see the second sketch I tell you. These three atoms, the bottom three atoms, which I am showing with the cursor, right? From right, it is third column, right? So these three will get and get aligned with the top three, right? And this, so like the see here, these three have been aligned with this, and the further their two more rows are coming and aligning with with the next row, next column of atoms, right? And let us assume there is one more dislocation like this, right? So now one dislocation has missed, right? One dislocation, one gap has one missing row of atoms, missing column of atoms has been occupied, right? That means one gap has been one gap has been occupied, right? So let us assume the a second row of missing or second column of missing atoms is coming into picture, right? Here, see in that last figure, as it is pushed further left and right like that. So this last row of see in the third sketch, you see I am showing with cursor the last row of atoms, the bottom three atoms, they come and occupy the second row, and along with the see the missing the gap is filled by these three atoms, right? So because of this, you see now in the top row, the shift is on from left to right, and then from bottom row the shift is from right to left, right? And now the gap which was here in the center now has come to the end, right? It has come to the end, right? Like that, see, we have shown only one dislocation here in the second sketch, and our first sketch. See, like that, so many dislocations will be there, right? So many dislocations, so many row of missing atoms will be there, right? Because of this only, in the case of metals, when the force is applied, a plastic deformation is taking place, right? When all the dislocations, when all the missing atom rows, when all the columns of missing atoms are occupied, then no more the deformation is possible, right? Then the deformation will not be possible any further, right? And so, see here in this case, there are no more dislocations here, right? In the last sketch, and beyond this, it is very, very difficult to deform it, right? So it attains a maximum strength here, right? After this, if you apply too much amount of load, it will only break at the mid plane, right? See here at the mid plane, it will only break rather than going rather than undergoing deformation, right? This is how in metals, in ductile metals, deformation is taking place. This is the mechanism of deformation in the case of metals, right? Deformation in metals is possible only by see when the when the columns of atoms are occupying the gaps, that means the dislocations are moving, right? So one column of atoms move to the next, and the next column of atoms move to the previous the adjacent one, and the last row of columns occupy the gap created after this has moved to the left, right? Likewise, deformation is possible only if dislocations are there, right? Only by movement of dislocations, deformation is possible, right? So this is a whole fundamental mechanism of strengthening in the case of metals, right? When large number of dislocations are there, strength will be low, and no more when no dislocations are there, the metal attains the maximum strength, and anymore the metal cannot be strengthened, right? That is the maximum when no dislocations are there. That is the maximum strength the metal can have, right? After that, it will only be breaking, right? And no more deformation is possible, right? So this mechanism, please be understanding very much, right? Only based on this, I will explain how in the composite strengthening is taking place, right? This is fundamentally in the case of metals and alloys, by dislocation movement only, deformation is taking place, and strengthening is also attained, right? So in the by movement of dislocations only, or moment of dislocations only is the strengthening mechanism in the case of metals and alloys, right? So with this, I'll go to the next slide, where in the case of where in that case a particulate metal matrix composite, we'll see how metal means like this dislocations will always be there, right? So in that case, we'll see in a composite how strengthening is achieved. See, this is a typical case of a metal matrix composite, right? These round ones are reinforcement particles, right? I have shown four reinforcement particles, and I have shown three dislocations here, right? One, two, three. The first one shown in red color, and the next adjacent one shown in green color, and the first one shown in the blue color, right? So let us assume three dislocations are there, right? So in between some gaps are also there. So okay, let us assume the movement of dislocations are shown as shown in the shown by the arrow markings here, right? So what let's see kind here in the stage one dislocations before passing the reinforcement particles, right? Let us assume, see from left side to right side, all these metal dislocations are pushed from left to right, right? That is what shown by these arrow markings, right? So the red one, the stage two, what happens on the right side? You see, please, right side of the laptop, right? So here the red color dislocation will try to push itself through the gap between the particles, right? So it will almost be breaking or almost be covering the particle like this, and it will try to cover the particle like this, right? And in stage three, you see that red particle, it has broken, that dislocation has broken, and one layer has enveloped the top particle, and the remaining half of the dislocation has covered the bottom particle, right? So now let us see here the curved dislocation passes between the particles and engulfs them, right? So this dislocation the red dislocation has broken into two, and half of it has engulfed the top particle, and half of it is engulfed the bottom particle, right? So in the next case, let us see when the dislocations are made to move further, the green one now enters into the gap between the particles, right? So here what happens? So it starts entering, and then in the stage three, what had happened? The green one dislocation also has broken, and it has covered and it has engulfed the bottom particle and the top particle. And in this case, there is almost no further gap between the top particle and bottom particle, right? So one layer is like this, the second layer is like this, but the bottom particle also the same case. Now the size of the particle has increased because dislocations have dislocated atoms have engulfed them, and the gap between the particle is no more there, and no more gap is there, right? And the blue dislocation, there is no chance for it to enter into it because there is no gap at all between the top and bottom particles, right? And this is the case where the composite has particulate composite has attained the maximum strength, and no more dislocation is able to pass through, right? So in this case, it has attained the maximum strength, and no more dislocation is possible, and beyond this, no deformation is also possible, right? So in the case of metal matrix composites like AL6061, right, when it is being deformed, right, the maximum deformation is possible only up to this point, and anymore there is no deformation possible. Normally, AL6061, yes, SIC composite and all, if you take, see, all wrought metal composites, if you take, what happens is the what happens is the see, yeah. So when these AL6061 aluminum, when it is melt, and as I told you, wrought aluminum generally has a melting temperatures are somewhere around 780 degrees centigrade or around like that. And in that case, what happens is if you melt it and pour into a mold, normally it will have too many number of dislocations in it, and also yeah, it will be porous. It will be having pinholes also in it, and it will be spongy also, right? So it will, and the wrought metals when it is poured in mold, it will not have sufficient strength, right? So it has to be secondary work. It has to be cold rolled, or it has to be extruded, or some deformation has to be done over that. Only then, and it should be compressed, right? Oh, wow. By compressing, the dislocations are made to come closer, or they are made to move, and also the pinholes are completely closed. And only by secondary working, the wrought metal composites attain the maximum strength, right? So by this way, when you secondary work, see the whole thing, enhancement of properties, by which I mean is the whole process explain you the secondary working only, right? Or deformation mechanism, right? Or that is cold working, right? Cold working or hot working, right? So here only by cold working or hot working, generally it is many times it is cold work, right? Or at a temperature around aluminum composites, or cold work at a temperature of around 400 degrees centigrade, right? So here these things, here the whole thing is cold worked here, right? So by cold working only, this wrought metal composite will obtain strength, and here at this stage 5, it has attained the maximum strength, and the further cold working will only break the composite, or the casting, and no more strengthening will be possible, right? So this is a stage at which it is attained the maximum strength by secondary working or cold working, and beyond this, any more deformation is not possible, right? This is how strengthening is. See here, as the gap is reducing. See in the case of you see in the case stage 3, the gap is more here. So the in stage 2, it would have easily the dislocation would have easily entered into the gap between the top and bottom particle, right? In stage 3, after stage 4, it would have found it would have been really a little more difficult for the dislocation to pass through a smaller gap, right? And in stage 5, no more gap is there, and the dislocation cannot pass through the top and bottom particle, and so this has the strength has begun reached the maximum level, right? So this is how enhancement of properties or strengthening mechanism is taking place in the case of ductile ductile metal X2 formed composites, where X2 form particulate composites, right? Ductile metal example is AL6061, right? So the one more thing you have to understand is in the case of AL6061, right? The silicon, silicon is the major one that is deciding whether a aluminum metal is cast or wrought, right? If silicon content is more than 6.6%, it's very high, like 6% or 6.5% or 6.7% or 7%, it is generally cast metal, right? In the case of wrought metal or ductile metal, the silicon content will be less than 1. Generally, it will be as low as 0.7 or zero point 0.6, like that, right? So, well, the role of silicon here in the aluminum metal is, in the case of cast metal, silicon is more like 6% to 7%, right? And this silicon, generally, silicon will reduce the melting temperature of the metal, right? So as silicon is more here only, in the case of A356, which is a cast metal, the temperature is the melting temperature is as low as 670 to 680 degrees centigrade. Whereas in the case of wrought metal, as the silicon content is very low, less than 1%, like zero point 0.6 or 0.7%, right? The melting temperature is very high here, say 780 or 800 or somewhere around that, right? So these are all the fundamental points that you have to remember, right? And with this, I'll go to the next slide, right? So now case 1 is over, right? where in case one, where I have taken a ductile metal matrix composite, and I have explained you how the strengthening mechanism play a role, right? Then case one is over now, right? I'll take the case two now. Fiber reinforced composite strengthening mechanism. In this case, you see, here the strengthening is achieved by the bonding strength between the reinforcement and, see, this is fiber, right? There are two fibers shown here, right? Some between the fiber and the matrix, the bonding strength will be there. The bonding strength gives you the strength, right? And also, if you see, these fibers are parallel, right? So this is called as a unidirectional fiber reinforced composite, right? So now we'll see how we can see. There are two things, right? One, we can load the composite along the direction of the fiber, right? That is one case. Another thing, we can load the composite perpendicular to the direction of fiber, right? Well, when you load it along the direction of fiber, the elastic models will be different, and when you the whole mechanism will be different. And when you load it perpendicular to the fiber, then the mechanism will be totally different, and the rule of mixtures and the calculation elastic modulus, everything, the formula, everything is different, right? So in this, two cases are there, right? One is to load along the direction of fiber, and another case is to load it perpendicular to the fiber, right? So along the length of fiber, we have a different elastic modulus, and along perpendicular to the fiber, the different elastic modulus is different, right? Whereas in the case of pure metals or alloys, in both the directions, whether it is any direction you take, in any direction, your elastic modulus will not change, right? Whereas in the case of fiber reinforced composite, depending upon the direction, the elastic modulus will change, right? We will see two cases. We will see the first case where we load it parallel, we load it along the direction of the fiber, right? So here you take, I have shown a small sketch here. Here I have shown the cross section of the composite. These are cross sections of the fibers, right? All are shown the circular cross sections, right? So many small fibers are there, right? There is a matrix also, right? And in this case, the title you please watch, overall elastic modulus. Overall elastic modulus means elastic modulus of the composite on the whole, right? uh, Modulus of unidirectional fiber reinforced composite in axial direction. Axial means along the length of the fiber. In this sketch, if you see the red color fibers, they are aligned perpendicular to the plane of the laptop or laptop screen, right? Or perpendicular to the screen, right? The fibers are running perpendicular to the screen. They are piercing through the screen, right? Now we'll add all these areas of the fibers, cross-sectional areas of the fibers, and then we'll take how much proportion of these fibers are there in the whole of the total area, right? Then that is called as VF is equal to volume fraction of fiber along the direction of overall modulus required, right? VF, volume fraction of fiber, right? VM is the volume fraction of matrix. In the total volume, you minus the total area of the fiber, you subtract the area of the fibers, then you will get the volume fraction of the matrix. See, area multiplied by length will give the volume, right? Whether both the fiber and the matrix will have the same length, right? So area multiplied by length, length is perpendicular to the screen, right? Laptop screen, right? So area of fiber multiplied by length will be VF, volume fraction of fiber, and area of the matrix material multiplied by length will be the volume fraction of matrix, volume fraction of matrix, right? EF is the elastic modulus of fiber, right? Elastic modulus of the fiber alone you take, you find out what is the elastic modulus, that is EF, right? Elastic modulus of fiber. Generally, elastic modulus of fiber is known, right? For all fibers, generally the manufacturer himself will give you what is elastic modulus, right? And EM is the elastic modulus of matrix. Let us assume you take polymer matrix composite. You know what is the elastic modulus of matrix material. That is also generally will be in the literature or will be available, right? For each, see if you take plaster of Paris, it has got a different elastic modulus, and if you take Kevlar, it has got a different elastic modulus of matrix. Like that, for different kinds of matrix, the elastic modulus will differ, right? So volume fraction of fibers is equal to Vf divided by total volume. Total volume is Vf plus Vm. Volume fraction of fiber plus volume fraction of matrix will be the total volume. You divide volume fraction of fiber by total volume, that will be the volume fraction of fibers, right? So then epsilon Ax. Epsilon Ax is nothing but the strain in the composite along longitudinal fiber, right? Along the direction of fiber, right? Epsilon F is equal to strain in fiber length, strain in the fiber alone, right? For unit load, right? And epsilon M is the strain in matrix along longitudinal direction of fiber, right? So strain in matrix, right? This is strain in matrix, this is strain in fiber, and this is strain in the overall composite, right? I'll go to the next slide now. So here, yes. So here, while considering the overall elastic modulus of the composite along the length of the fibers, we should note that strain in the fiber is equal to strain in matrix. See, please note that the fiber is attached to the matrix with bonding strength, and there will be a bond between fiber and matrix. When the fiber extends, the matrix also will extend along with that, right? When the fiber is compressed, the matrix also will compress along with that. So the fiber and the matrix undergo equal strain only, right? So when these two undergo equal strain, right, the overall composite also undergo equal strain, right? So the fundamental governing condition is epsilon AX. Epsilon AX is nothing but the overall strain in the composite is equal to the strain in the fiber, that is equal to strain in the matrix. With this condition, with this governing condition only, we are going to derive, we are going to estimate what will be the, we'll find out, we'll, at the end of it, we'll derive a formula based on this condition only to find out, to estimate what will be the elastic modulus of the overall composite, right? Here, see, normally elastic modulus E is equal to stress by strain, right? So E should be here. E is equal to, this is strain, epsilon AX divided by, sigma AX, it is divided by epsilon AX, right? I'm sorry, this F is wrongly printed here. So it is epsilon AX, right? So now this the elastic modulus EX is brought down here, and the strain has been brought to the other side, right? So epsilon AX, you please ignore this small f, so in the suffix, right? Epsilon AX is equal to sigma AX by EAX, right? Like that, epsilon F is equal to sigma F, stress in the fiber divided by elastic modulus of the fiber. And then a strain in the matrix is equal to stress in the matrix divided by elastic modulus of the matrix, right? So from this, we arrive at this equation, right? So from here, sigma x, you bring up this, you bring the EAX, the other side of the equation. So sigma AX is equal to elastic modulus into strain, right? So sigma AX is equal to EAX into epsilon AX. Sigma F is equal to EF into epsilon F. Sigma M is equal to EM into epsilon M, right? So here we know that say stress is nothing but force per unit area, right? So here we should we should the formula the load the for the basic the, condition is the load in the composite material is equal to load in the fiber plus load in the matrix, right? But as we have taken unit area, right, stress in the composite, overall composite, because for load per unit area is stress, right? So we'll take instead of load, we'll take load per unit area, right? So unit area of the overall composite. So sigma AX is equal to fraction of fiber into volume fraction of fiber into sigma F plus 1 minus volume fraction of fiber into sigma M, right? Now, considering the set of equation 3 and 4, see, this is equation 3, this is 4, right? So, what we do for sigma x, we will substitute from 3, right? So, for all, so what will happen? So, this sigma x will become Ex into epsilon x, right? And here for sigma f, we will substitute from here, from equation 3, from center, Ef into epsilon f, right? And here Em into, so for sigma m, we will substitute Em into epsilon m, right? But epsilon ax, epsilon f, epsilon m are equal as per condition equation 1 on the top, right? I am showing with the cursor. Okay. So epsilon ax, epsilon af, and epsilon m being equal, they will all get cancelled, right? And the resulting equation becomes EAX, that is overall modulus of the elastic modulus of the composite is equal to volume fraction of the fiber into elastic modulus of fiber plus 1 minus volume fraction of fiber into, that is nothing but volume fraction of matrix multiplied by elastic modulus of matrix, right? So this equation, see here, once you know the volume fraction of fiber and elastic modulus of fiber and elastic modulus of matrix, we can very easily find out by we can very easily calculate with the help of this equation what will be the elastic modulus of the overall composite. And so this particular equation is called as rule of mixtures, right? Why it is called rule of mixtures? This equation is based on the volume fraction of fiber and the volume fraction of matrix. The volume proportion, the mix of proportions of the fiber and the mix of proportion of the matrix together the whole thing is based on the mix of the fraction of fiber and fraction of matrix, and so it and the way the fraction of fiber and the fraction of matrix are mixed together, the whole equation is based on that. So it is called rule of mixtures, right? So this rule of mixture is for this. See, this equation will give you the elastic modulus in the along the length of the fiber, right? Along the length of the fiber, or along the length of the fiber, right? So if you see if the composite is loaded along the length of the fiber, then the governing equation will be this, right? Then as per this formula, we can find out the elastic modulus of the composite in the along the length direction of the fiber, right? The same thing, if you see, we'll go to case 2 now, right? So this is case, drawing pool, yeah. Okay, we'll take the case. See, here the perpendicular to the plane, yeah, if it is loaded, it is along the length of the fiber, right? If it is going to be loaded from right to left, or from left to right, or from top to bottom, or from bottom to top, then the loading is transverse. Transverse means perpendicular to the fiber, right? That perpendicular to the orientation of the fiber, right? Perpendicular to the orientation. In this direction, right? Yeah, for example, from bottom to top, if you are going to load it, then we will see how we will find out the elastic modulus in the case of case 2, right? I'll go to case 2. So in that case, we call the overall tensile strength of the composite is given by sigma transverse. I have put it as sigma transverse, right? And sigma f is the tensile strength of the fiber, right? Sigma m is the tensile strength of the matrix, right? Now we'll see in this case. See, I'll come to the sketch once again, right? See, if you load it from left to right to left, See, what happens is, see, if you take a plane here, if you take a before this five between the fibers and the with the matrix, if you take a plane, what how will you find this one stress? This load divided by the area in this direction, right? That will be the stress, right? If you take in along the fiber also, then also if you want to find out what is the stress, it is once again load by area only, right? So whatever may be the section, the stress is only load divided by area, right? And the fraction of the fiber is so less generally, right? And it is so thin also, and so here the strain in the fiber along the diameter is very very low, and so strain in the matrix once again it is not it is not going to make so much of difference in the stress, right? So because of this, now based on this, we'll see how we derive the see finally we'll be deriving in this case the elastic modulus along transverse direction, right? So we'll see how we derive it now. So nomenclature is sigma transverse is tensile strength to the composite in transverse direction. Sigma F is the tensile strength to the fiber. Sigma M is the tensile strength to the matrix, right? Sigma transverse is equal to that is overall stress is equal to overall strength is equal to overall stress is equal to overall stress in the fiber, that is equal to stress in the matrix. So I should not have put it as tensile strength. It should have been tensile stress. I am sorry, this is not strength. Please replace all these strengths by stress, right? It is wrongly given here, right? So tensile stress in the composite, tensile stress in the fiber, tensile stress in the matrix, right? So all these things will be equal, right? Okay, now sigma f is equal to, as we found in the other case, so for sigma, see, elastic modulus EF is equal to sigma f by epsilon f, right? It is brought to the other side. So sigma f is equal to EF into epsilon f. Sigma m into is equal to EM into epsilon m, where EM is the elastic modulus matrix and epsilon m is the strain in the matrix, right? So epsilon transverse is equal to, how we do it? So F into here. See in this case, what we have done? Yeah. Here the governing condition is fraction of fiber into overall strain is equal to fraction of fiber into fraction of strain in the fiber plus 1 minus f, that is nothing but fraction of matrix into epsilon m, right? So here there the stress was the overall the first case one, the overall stress was is equal to stress in the fiber plus stress in the matrix, whereas here strain in the overall composite is equal to strain in the fiber plus strain in the matrix, right? So now, from this equation, what happens is EF is equal to E transverse is equal to sigma transverse by epsilon transverse, right? So, see what we want to find out, E transverse we want to find out, right? Elastic modulus along in the perpendicular transverse direction we want. So that is equal to sigma transverse divided by epsilon transverse, right? So now the epsilon transverse from equation 3, if you substitute here, sigma transverse divided by this part will all the whole come down here. Okay, and see what we do next is we now divide this equation throughout by sigma f, right? Then what will happen? Or we bring down the sigma f. You see from top, from numerator, we bring it to the denominator. So what will happen? F into epsilon f divided by sigma f it will become plus 1 minus f epsilon m divided by sigma f, right? So if you see in the bottom equation, right? See, huh? So F into, see, epsilon F divided by sigma F, right? Whereas here from there, basically, See from from this equation one, right? What you have found? Sigma f is equal to sigma m, right? So in this this slide, right? So as sigma f is equal to sigma m, we replace this. See this sigma f which is coming down here, right? We replace that sigma f by sigma m here, right? So what happens is epsilon m by sigma m. What is that? From here, epsilon by sigma m is nothing but em, right? Epsilon f by sigma f is nothing but epsilon f by sigma f. See, sigma f, sigma f by epsilon f is equal to 1 by ef, right? Sigma m by epsilon m by sigma m is equal to 1 by ef from this equation, right? That we will substitute for these two terminologies, right? Next. See, by substituting that, the equation becomes fraction, volume fraction of fiber divided by EF plus 1 minus F divided by EF, right? So the whole equation now has become 1 divided by the whole thing in brackets, right? F by EF plus 1 minus EF divided by EF, right? It is uh, because the epsilon f by sigma f is equal to 1 by f. These things we have substituted, see, in this, at the bottom of the equation here, right? We have, see, epsilon f by sigma f, we have substituted by this term, 1 by ef, right? And the other term by this, right? Now, see, if you find epsilon transverse, here the equation itself is totally different here, right? Elastic modulus in the transverse direction is totally different here from case 1, right? So see case 1, if you see epsilon f is equal to the rule of mixtures gives you this formula, right? In case 2, for finding the transverse modulus along perpendicular direction, the rule of mixtures is this, right? So the rule of mixtures in general is not the same for the fiber reinforced composite in all directions, right? From when the direction is changed, the elastic modulus also changes, right? So this elastic modulus is for loading perpendicular to the fiber, and the other one is loading the composite along the length of the fiber, right? And so now the session is over, right? And if any doubt is there, if for any clarification is needed, please kindly ask your clarifications. I am ready to answer your questions and clarifications sorted. Now I'll close and come to the screen. If anybody has got any doubt, please ask me. Anything regarding composite, not only this. Any doubt you have. What is the role of matrix in composite material, sir? The role of matrix in composite material is to hold the reinforcement, right? Is to hold the reinforcement. For example, if fibers are there, the fibers will be flexible, all the fibers are kept in alignment by the matrix. And one thing is it kept in alignment by the matrix, and the load that is applied on the matrix is transferred through the matrix to the fibers. The fibers only take the major amount of load, but the role of the matrix is to transfer the load from matrix to the fiber, right? So can you give me a fair example for matrix metals? Aluminum, metaphor, metal matrix, aluminum, copper, and these two are generally the examples. Magnesium is also an example, right? Whereas for polymer matrix composites also there, where in the case of polymer matrix, Kevlar is there, and it was, in the polymer matrix, then there is two more classifications are there. One is called as thermoplastic, and another is called thermo set. In the case of thermoset, liquid resin will be poured into the fiber or mixed along with the particles, and it will be made to set. it will get cured, and liquid resin will get evaporated, leaving you leaving a solid composite finally, right? That is called thermoset. In the case of thermoplastic, the difference between thermoplastic and thermosetting is it is like cement. It is set in the case of thermoset. The resin, yeah, resin will be poured into the fiber, right? Bundle of fibers, or yeah, particles will be mixed in the resin, and it will be poured in the mold, and it will be allowed to set. Over time, the resin will get evaporated and go out. That is thermoset resin, right? Whereas for that exam, one exam, so many exam like polyvinyl chloride is there, right? And that is called PVC, right? And this one for thermoplastic. The case of thermoplastic, it can be remelted and used, whereas in the case of thermoset, once it is formed, it cannot be remelted and used, right? So another matrix is carbon-carbon matrix. In the case of carbon-carbon matrix composite, the matrix is also carbon, fiber is also carbon, right? So in the case of carbon-carbon matrix composite, carbon is the matrix, and in the case of ceramic matrix composite, ceramic material is the matrix. There also there in the case of ceramic matrix composite, the matrix is also ceramic, fiber is also ceramic, right? So ceramic can be Al2O3 or SiC, anything like that. Any other question? So what's the difference between FRP and MFG, sir? FRP and see, in the case of metal matrix composite, matrix is the metal. FRP means fiber reinforced plastics. FRP matrix is plastic. And metal, in the case of metal matrix composites, generally it will be particulate metal matrix composites only. Normally fiber reinforced metals are not there. In the case of plastics, both particulate and fiber reinforced are there. So which is the most advanced applications of composites? Carbon-carbon matrix composite. Because see, carbon-carbon composite is the lightest of all the composites, right? It has got the highest strength to weight ratio, right? For unit weight, it gives the highest possible strength, right? And it is the lightest composite, right? Even it is lighter than the magnesium, right? Very, very light, and it is used for space applications and aerospace applications, and for the one application, the main application is, yeah, the aircraft brakes, landing gear brakes, right? So in the case of aircraft landing gear brakes, it is called landing gear brake. It is not simply called as brake, right? It is called landing gear brake, right? So in the case of landing gear brakes, the brake shoes and as well the brake pads especially are made with carbon-carbon composite, right? In this case, earlier it was made with copper plate. The brake pads were made of the brake shoes and brake pads were made up of copper and asbestos, right? In that case, copper, yeah. So there, the weight of the copper was very high, right? Whereas, and one more thing, with carbon-carbon matrix composite, it can transfer the heat very, very quickly, right? Even it has got much higher thermal conductivity than copper, right? So, in the case of landing gear brakes, for example, for one brake, in the case of Boeing aircraft, 700 kg of load for one Boeing aircraft, 700 kg of load can be reduced by going in for carbon-carbon composite instead of conventional brakes, right? So by doing that, see, for example, if 700 kg can be reduced, approximately 10 passengers can be accommodated more, right? So this is the advantage of carbon-carbon composite. Ah, sir, this is devolution, sir. Tell me, please. Is it possible to Yeah, it is very much like particulate composite only. It is possible. The same formula you can use for dispersion strengthened composite also. But how to predict the No, no, no. See, you wanted elastic modulus only, right? You wanted to find out the elastic modulus of the particulate composite. There, see, instead of uh, normally, you have to find out. Finding the area of particulates is very difficult, right? Because if you observe in scanning electron microscopy picture, right, the area of the particles can be approximately found, right? So if you know the if you know the weight fraction and size of the particle, right, you can approximately estimate what will be the area fraction of the particles in a given cross section, right? So based on that only you can calculate. But one thing, it will be approximate only. You cannot exactly predict it. Yeah. Huh. So, see, nanocomposite is like your precipitated metals, right? Precipitation strengthening in the metals, right? Precipitation strengthening, I think many of you, I will just explain what is precipitation strengthening, right? So, if you take aluminum and all, once you cast it in a mold, then what you will do, you will heat treat it, right? Or when you heat treat it, the physics, for example, you do some solutionizing at 540 degrees centigrade, you will heat the metal and put it in a salt bath, right? And then you will take it and you will take it and put it in a furnace where it is maintained at 180 degrees centigrade, right? For about 18 hours or something like that, right? That is called as age hardening, right? During which time what happens is the intermetallics and the intermetallic compounds will settle in groups, along the inside the inside the aluminum cross section, right? So these things will act as small particles, right? These particles will not allow the dislocations to move, right? Because of this, strengthening will take place, right? Strengthening will be there, right? The strengthening mechanism is because of the dislocations not being able to pass through the settled intermetallic compound, right? So, like composites, in the case of precipitation hardening also, the same mechanism, strengthening mechanism is there, right? So, in the case of if you take nanocomposites, it will be the same case as precipitation hardening, because in the case of precipitation hardening also, the precipitates are the nanoscale only. Okay, okay, okay. Uh, Yeah, many times it is beneficial because it give some let us assume the normally the reinforcing particles have lower thermal expansion, right? And the aluminum matrix will have higher thermal expansion, right? And as it cools from higher temperature from lower temperature to lower temperature, the particle will be in compressed state, right? Because aluminum will cool shrink more, whereas the ceramic particulate will not shrink that to that extent. So aluminum will be keeping the particles in the compressed state, right? So this will act to something like pre-stressing, and so it will increase the strength only. It is advantages only. Thank you, sir. Thank you, sir. Okay. Thank you. Any other query?
Thank you, sir, for your nice informative section, sir.
Okay.
Very much a lot.
Any other query? Any other query? No more queries? Okay. Okay.
Good evening to I take great honor to propose prototype for this memorable occasion. First and foremost, I'd like to thank the MFG God for making this community development program on advances in materials for their economic purpose. Next, I would like to thank our honorable chairman, Sri K. respected managing director, Dr. Chief Finance Officer, Dr. on behalf of Rohit College of Engineering and Technology, I extend my personal thanks to them for their continued support. Next, a heartful thanks to our great principal, Dr. Rohit, not only for spending his time with us today, but also for encouraging us to achieve many videos. Thank you, sir. Now I take this golden opportunity to thank our respected person, Dr. Annamalai, Professor, Department of Manufacturing Engineering, Annamalai University, who honored this program with his inspirational thought and gracing today's webinar on fundamentals of composites. On behalf of Rohit College of Engineering and Technology, thank you, sir, for your input and valuable information about composites. Next, a heartful thanks to the state coordinator, Dr. Madhusuri, for his continuous support for us. Thank you, sir. I also extend my special thanks to the Culture Department of Music and Another of this program, Dr. J. Jessica. Thank you, ma'am. I would like to thank my colleagues, Mr. C. Petiwell, Mrs. Tangam, Assistant Professor of Physics, for your cooperation in making this program a grand success. I sincerely thank all the participants for purifying this program. Without you, this program would not be a success. On behalf of Rohit College of Engineering and Technology, thank you to all. Once again, I thank Alendra for hearing me.
Thank you all. Thank you all. Wish you all good luck. Thank you.
Thank you, sir.
We'll close the session.
Thank you, sir.
ఎక్కడ యాడ్ చేయదు పాருங்க ఎక్కడ యాడ్